You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Security Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. The goals of automation in security are centered on making operations faster, safer, and more scalable. Cybersecurity teams face constant demands, from investigating alerts to patching vulnerabilities to responding to incidents. Many of these tasks are repetitive and consume valuable time. Automation helps by executing them consistently and at machine speed, reducing reliance on human memory or manual effort. Another goal is minimizing human error. Even skilled analysts make mistakes when fatigued or under pressure, but automation enforces consistency every time. Finally, automation allows scaling. As organizations grow, the number of systems, alerts, and logs multiplies beyond what humans alone can handle. Automation bridges that gap, ensuring security controls expand in lockstep with infrastructure. The mission is not to remove humans, but to let them focus on higher-value analysis and decision-making while machines handle the repetitive groundwork. In this way, automation becomes a force multiplier, enabling small teams to defend large environments effectively. Common areas of automation in security include triage, enrichment, remediation, and reporting. Triage automation sorts and prioritizes incoming alerts, filtering out obvious false positives and flagging those that matter most. Enrichment adds context to alerts by automatically gathering details such as threat intelligence lookups, user information, or system status, so analysts do not waste time chasing basics. Remediation refers to automated responses, such as quarantining infected endpoints, blocking malicious IP addresses, or disabling compromised accounts. Reporting automation streamlines compliance by generating audit-ready reports, pulling from logs and security tools without requiring hours of manual work. Each of these areas demonstrates how automation not only saves time but also improves accuracy. Instead of hundreds of raw, noisy alerts, analysts receive curated, context-rich findings ready for investigation. The result is faster response, fewer errors, and more resilient operations. Without automation, teams often drown in repetitive tasks. With it, they can focus on strategy and threats that truly require human insight. Scripting is often the entry point to automation, and best practices ensure those scripts are safe and reliable. One principle is idempotence, meaning a script can be run multiple times without causing unintended side effects. For example, if a script is meant to disable a compromised account, running it twice should not cause errors or double actions. Another principle is using safe defaults, where the script assumes conservative actions unless explicitly told otherwise. A script should never delete data or reboot systems by default without clear confirmation. Dry run modes are another safeguard, allowing a script to show what actions it would take without actually executing them. This prevents accidents during testing and provides confidence before live use. Collectively, these practices reduce risk and make scripts more trustworthy. For beginners, it helps to think of scripting like designing power tools. Powerful, yes, but only safe if equipped with guards, safety switches, and controls that prevent accidents during normal operation. Credential handling in scripts is a common security pitfall and must be managed carefully. Hard-coding usernames and passwords directly into scripts is a dangerous practice, as those credentials often end up in version control, logs, or shared files where they can be stolen. Instead, scripts should retrieve secrets securely at runtime from vaults, APIs, or through ephemeral tokens that expire quickly. Secrets vaults, such as HashiCorp Vault or cloud-native services, centralize secret storage, enforce access policies, and provide audit trails. By leveraging these systems, scripts can remain clean of static secrets while still functioning seamlessly. Ephemeral tokens add another safeguard, ensuring that even if one is intercepted, it becomes useless after minutes or hours. The guiding rule is simple: never let sensitive secrets linger in plain text. For learners, this can be compared to using a hotel room keycard that stops working after checkout. By relying on vaults and temporary tokens, scripts avoid becoming long-term liabilities. Input validation and error handling are also critical for safe scripting. Without validation, a script may accept unexpected or malicious input, leading to unintended consequences such as deleting the wrong files or shutting down the wrong system. Secure scripts check their inputs rigorously, rejecting anything that does not conform to expected formats. Error handling ensures that when something does go wrong, the script fails safely rather than catastrophically. For example, if a script encounters a missing file, it should log a warning and exit gracefully, not proceed with destructive defaults. In high-stakes environments, error handling can mean the difference between a minor inconvenience and an outage. Secure automation anticipates failure and contains it, much like airbags in a car reduce the damage of a crash. By combining validation with strong error handling, scripts transform from brittle, risky tools into dependable building blocks for larger automated workflows. Testing strategies for scripts mirror those used in software development, but tailored for automation tasks. Unit tests validate individual functions or logic blocks, ensuring that small pieces of the script behave correctly. Integration tests confirm that the script works properly when interacting with external systems, such as APIs or databases. Sandboxed dry runs allow scripts to execute in test environments that mimic production, ensuring behavior is correct without risking live systems. This structured testing prevents costly surprises in production, where even a small bug in a script could lead to outages or security gaps. Testing also builds confidence in automation. Teams are more willing to rely on scripts if they know they have been rigorously validated. For learners, testing can be compared to rehearsals in theater. Actors practice scenes repeatedly to catch mistakes before performing in front of an audience. Similarly, scripts must be rehearsed in controlled conditions before being trusted with real systems. Version control and code review bring discipline to scripting. Using version control systems like Git ensures that every change is tracked, recoverable, and auditable. If a script update introduces a problem, teams can roll back to a prior version quickly. Code review adds another layer of safety by having peers examine scripts for errors, inefficiencies, or security risks before they are deployed. This process catches mistakes early and spreads knowledge across the team. It also reduces the risks of shadow automation scripts written by one person, undocumented, and forgotten until something breaks. By formalizing script development with version control and review, organizations ensure that automation is treated as critical infrastructure, not as ad hoc utilities. For learners, this is like keeping blueprints for every repair in a building. If someone needs to retrace steps later, the documentation is there, and every change is recorded for accountability. Logging and observability are vital for troubleshooting and auditing automated actions. Without logs, when a script fails or produces unexpected results, administrators are left guessing what happened. Good automation logs every major action, including inputs, decisions, and outputs. Observability extends this by aggregating logs into dashboards that show trends, failures, and performance metrics. This visibility ensures that automation is not a black box, but a transparent process that can be monitored and improved over time. Audit logs also support compliance, providing proof of what actions were taken, when, and by whom. For example, if an automated script disabled user accounts, logs should show exactly which accounts were affected and why. This record creates accountability and supports investigations if issues arise. In short, observability turns automation from invisible background tasks into traceable, reliable systems that can be trusted at scale. Change control is another requirement when automation affects production systems. Just like manual changes, automated actions must go through review, approval, and scheduling to avoid disruptions. Change control processes ensure that automation does not introduce untested or risky modifications. For example, a new remediation script should be approved in a test environment before being added to production workflows. Skipping change control may lead to outages or, worse, security breaches caused by unreviewed code. Automation should not bypass governance. It should be subject to it. For learners, change control can be thought of as having a checklist before flying a plane. Even if the autopilot system is excellent, humans must still review and approve its use to ensure safety. By embedding automation into existing change processes, organizations maintain stability while still reaping the benefits of faster, safer operations. Avoiding brittle automation is another best practice. Brittle scripts are those that break easily with even minor changes in the environment, such as new log formats, renamed APIs, or updated configurations. To prevent this, automation should be designed with resilience in mind, using patterns like retries, error tolerance, and abstraction layers. For example, instead of parsing fragile log file strings, a script should consume structured data from an API. Resilient automation adapts to minor changes without collapsing, making it dependable in dynamic environments like cloud or DevOps pipelines. Brittle automation wastes time because it constantly requires fixing and undermines trust in automation programs. Resilient patterns ensure that automation scales sustainably, growing alongside the environment instead of fighting it. For learners, the analogy is building with flexible materials. A rigid structure may look strong but cracks under stress, while a flexible one bends and adapts, lasting far longer under real-world conditions. Even with strong automation, high-risk actions still require fallbacks and human-in-the-loop checkpoints. For example, automatically disabling hundreds of user accounts after a suspicious event could cause massive disruption if the trigger was incorrect. Instead, automation can prepare the changes, log the justification, and then require human approval before execution. Fallbacks also mean having manual alternatives if automation fails or produces errors. This prevents over-reliance on automation and ensures humans retain ultimate control over sensitive operations. For learners, think of this like cruise control in a car. It handles routine driving, but the driver must stay ready to intervene if conditions change. Automation should never remove human oversight from decisions that carry major business or security consequences. By designing fallbacks and checkpoints into automation, organizations ensure that speed and efficiency never come at the cost of safety and trust. A practical way to begin applying these principles is by selecting one frequent manual task and converting it into a script. Triage tasks, such as checking if an IP address is on a threat list, are excellent starting points. The script should include a dry run mode so it can be tested without side effects. Credentials should be handled through a vault, not embedded in the script. A test harness, or framework for simulating inputs and validating outputs, should be built around it. Once tested, the script can move into production to save analysts time. This exercise demonstrates how automation turns repetitive, error-prone tasks into consistent, reliable processes. By starting small, teams gain confidence, prove value, and establish practices like dry runs, vault integration, and testing that will carry into larger projects. It reinforces that automation is not an all-or-nothing leap. It is a series of small, careful steps that build momentum toward robust, secure workflows. Orchestration patterns expand automation from individual scripts into coordinated workflows that run across systems. Event-driven orchestration uses webhooks or triggers from other tools to kick off automation in real time. For example, when a suspicious login is detected, an event-driven workflow can automatically enrich the alert, disable the account, and notify analysts. Scheduled jobs represent another pattern, where tasks run at fixed times, such as nightly scans or weekly report generation. Queue-based workers provide scalability by distributing tasks across multiple workers, ensuring the system can handle spikes in workload. For instance, if a flood of alerts arrives, a queue allows workers to process them steadily without overwhelming resources. These orchestration patterns ensure automation is not just reactive, but also proactive and scalable. They form the backbone of security orchestration, automation, and response platforms, allowing complex playbooks to be executed consistently without requiring human initiation every time. Preventing repeated or duplicated actions is critical in automation, and this is where idempotency keys and deduplication come into play. An idempotency key ensures that if the same request is sent multiple times, it will only execute once. This prevents duplicate actions, such as disabling an account twice or repeatedly quarantining the same device. Deduplication goes further by identifying repeated events, often caused by noisy systems or overlapping alerts, and consolidating them into a single action. Without these safeguards, automation can easily spiral into chaos, with duplicate actions creating outages or confusion. For example, if an attacker attempts a brute force attack that generates thousands of alerts, deduplication ensures automation responds once, not thousands of times. This keeps systems stable and prevents wasteful or harmful duplication. In essence, idempotency and deduplication act like governors on an engine, keeping automation precise, efficient, and safe even under high pressure. Deciding what to automate fully and what to leave for human approval requires establishing safe automation boundaries. Some actions, like enriching alerts with IP reputation data, can be fully automated because they are low risk. Others, like disabling hundreds of user accounts or deleting suspicious files across servers, may require human review. The key is understanding impact. Actions with limited blast radius can be automated freely, while those with potential for widespread disruption need oversight. This balance ensures automation speeds up routine tasks without creating accidental disasters. For learners, it is useful to think of automation boundaries like autopilot in an airplane. Autopilot can handle routine cruising safely, but landing in bad weather still requires a pilot's judgment. Safe boundaries allow automation to handle the predictable, while humans handle the exceptional. Clear boundaries also reassure stakeholders that automation enhances safety rather than removing necessary human control. Observability for automation means monitoring not just the outputs, but the health of the automation itself. Metrics such as task completion rates, error counts, and latency help identify bottlenecks. Service-level agreements, or SLAs, define expectations, such as how quickly automation must respond to critical alerts. Dashboards provide real-time views of system health, allowing analysts to spot failures immediately. For example, if a remediation script that normally takes seconds suddenly slows to minutes, dashboards highlight the delay before it causes backlogs. Observability transforms automation from a black box into a transparent, measurable system. Without it, teams may assume automation is working when in fact silent errors are leaving gaps. With observability, automation becomes predictable, auditable, and improvable. Just as monitoring the vital signs of a patient guides medical decisions, monitoring the vital signs of automation ensures it continues to perform reliably as environments evolve. Secrets handling must evolve alongside automation pipelines. Static, long-lived tokens embedded in automation create major risks because they can be leaked or stolen. Instead, organizations should enforce secrets rotation and minimize token lifetimes. Ephemeral tokens that expire within minutes or hours provide a strong safeguard, ensuring any exposed credential quickly becomes useless. Automation systems must also handle rotation gracefully, retrieving new credentials seamlessly without manual intervention. For example, a build pipeline can fetch a fresh token from a vault each time it runs, discarding it at the end. Rotation also supports compliance by proving that credentials are not static and unmanaged. By automating secrets rotation, organizations remove one of the most common weak points in automation. The principle is simple. Automation should never rely on permanent keys. Instead, it should rely on dynamic, short-lived credentials that limit exposure and strengthen trust. Dependency management is another cornerstone of resilient automation. Scripts often rely on runtime libraries, external APIs, or system utilities. If those dependencies change without warning, automation may break. Managing dependencies means pinning versions, packaging scripts with the exact libraries they require, and testing against updates before deployment. Containerization can provide predictable execution environments, ensuring scripts behave consistently across systems. Without dependency management, automation becomes brittle, collapsing whenever the environment changes. With it, automation becomes portable, predictable, and easier to maintain. For learners, dependency management can be compared to cooking with specific ingredients. If you expect sugar but someone substitutes salt, the recipe fails. By controlling ingredients versions and libraries, automation ensures consistency. Organizations that ignore dependency management often find themselves firefighting broken scripts, while those that embrace it build reliable systems that scale confidently across environments. Canarying automated remediation is a technique that reduces the risk of large-scale mistakes. Instead of applying an automated fix across an entire environment, the system first tests it on a small subset of targets. If the remediation works as expected, it can then roll out broadly. If it fails, the scope of damage is limited to the canary group, and the process stops for review. This mirrors practices in software deployment, where canary releases protect production systems. For example, if an automated workflow is set to quarantine devices showing malware, a canary rollout might first apply it to 10 devices before expanding to hundreds. This approach prevents runaway automation from creating outages or disabling legitimate systems by mistake. Canarying reflects a cautious mindset. Automation is powerful, but with that power comes responsibility to minimize risk. By testing broadly impactful actions in small doses, organizations keep control and reduce fear of automating critical tasks. Integration with SOAR platforms, security orchestration, automation, and response brings automation under standardized governance. Instead of ad hoc scripts scattered across teams, SOAR provides centralized playbooks, approval workflows, and monitoring. Playbooks define step-by-step automated responses to common incidents, such as phishing investigations or malware containment. Governance features ensure approvals, audits, and versioning are applied consistently. SOAR platforms also integrate with CIEE and ticketing systems, tying automation directly into detection and case management. This creates an end-to-end incident response pipeline where alerts are detected, enriched, acted upon, and documented automatically. For learners, SOAR can be seen as turning isolated instruments into a symphony. Scripts and automations that once acted alone are now orchestrated together, guided by a conductor, with every note tracked. This integration elevates automation from useful tools to formalized processes that align with organizational policies and compliance needs. Rollback and compensation actions are safeguards when automation produces undesired effects. Mistakes are inevitable, and automation might disable the wrong accounts, block legitimate traffic, or delete important files. Rollback allows reversing those actions quickly, restoring the system to its previous state. Compensation goes further, adding corrective measures to repair damage caused. For example, if a workflow disables user accounts incorrectly, rollback restores them, while compensation might notify affected users and re-enable their access tokens. Designing rollback and compensation into automation workflows ensures resilience. It acknowledges that errors will happen but prepares structured responses instead of improvisation. For learners, think of it like having an undo button. Without it, every automation error becomes a crisis. With it, errors become manageable and recoverable. Rollback is the safety net that makes teams confident enough to automate boldly, without fear of irreversible mistakes. Documenting automation runbooks and assigning maintenance ownership prevents orphan tools. A runbook describes what an automation does, when it should be used, and who owns it. Without documentation, scripts often outlive their creators, leaving others unable to maintain or troubleshoot them. Ownership ensures accountability, with clear responsibility for updates, monitoring, and retirement when no longer needed. Runbooks also help during incidents by guiding analysts through the steps automation will take, reducing surprises. For learners, documentation is like the manual for a complex machine. Without it, operators are left guessing at controls. Organizations with strong documentation avoid the tribal knowledge trap, where only a few individuals know how automation works. This reduces risk and improves resilience, ensuring automation remains sustainable over the long term. Security coding standards apply to automation scripts just as much as to software. Scripts may be small, but they can perform powerful actions that impact critical systems. Standards such as code linting, peer review, and static application security testing, SAST, help catch errors and vulnerabilities early. For example, linting tools highlight unsafe coding practices, while SAST tools scan for hard-coded secrets or insecure library usage. Applying these standards ensures automation is not only functional, but also secure by design. It also provides auditors and stakeholders with confidence that automation adheres to governance requirements. For learners, this is like building safety codes into construction projects. Even a small shed must meet safety standards, because collapse is still dangerous. Likewise, automation scripts must meet coding standards because they often act with privileged power, where small errors can have outsized consequences. Ultimately, robust automation in security is about balance. Safe defaults prevent catastrophic errors. Secrets handling keeps credentials out of reach. Testing builds confidence. Observability ensures transparency, and fallbacks preserve human oversight. Together, these practices create a resilient foundation where automation can handle the routine while humans focus on exceptions. The mission is not to automate everything blindly, but to automate wisely, humanizing the moments where judgment is required. Mature automation programs grow incrementally, starting small, learning from mistakes, and scaling cautiously with safeguards in place. For organizations, the payoff is enormous: faster response times, reduced analyst fatigue, and more consistent defenses. For learners, the key takeaway is, this automation is not about replacing people, but about empowering them. By automating the routine and reserving human expertise for the extraordinary, security operations become both more effective and more sustainable. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.